on soon. Hope so. Let's start from the slide here. Charles, right? Yeah. All right. Well, I'm going to go in the morning. Why they open the door, then lock it back. Makes no sense. All right. Now, any questions on anything we've done so far? One question I have for you: has everyone received the first quiz? Any of you who didn't get the first quiz? Good. All right. Other thing, the announcements. The library on the Birmingham campus, in the Birmingham West campus, has had up for most of this month I think a pretty impressive exhibit from Holocaust survivors from the state of Alabama. I think 40 Holocaust survivors from the state of Alabama, their art, their photography, from what I understand, a very impressive exhibition. So if you can get by there, go see it. I believe that, let's see, Monday may be the last day that it's being exhibited. So if you can, get by and see it. It's really good. Also, our women's volleyball team has a number of matches in the works. I think they played last night at home against Bevel State, maybe, or no, one of the other schools. And then I think today they're traveling to Bevel State, Fayette, Alabama, for a match up there. And then over the weekend they've got a match or a tournament over in LaGrange, Georgia. LaGrange, Georgia, however you say it. Now, I don't know if y'all are aware of this or not, but our volleyball team last year won the most games in school history, matches in school history. They were quite good. And I think they got, maybe half of them back and some new recruits. One of our own is on the volleyball team. It may be why she's not here today. I just called her name, and now I think it was Katie. That may be they're leaving to go to the match in Fayette, Alabama sometime today. Wouldn't think it would be this early, but maybe they were. Could have had a time change. But anyway, if you can, so when it's a home game, match, or if you happen to be in one of the towns where they're having a tournament or playing, stop by to see them and cheer them on, because I think you'll find they're quite good, worth the watch. See, anything else? NASA Community College Aerospace Scholars Program is, I think you'll see various announcements posted on the walls. They're accepting applications through, I think, October 16th. Can I get your name, please? Sorry. Raquel. Got it. Now finding you. There you are. Okay. Anyone else come in since I called roll? Okay. Let's see if there were others. This is a bit more on a personal note for me. Normally I have office hours on the Birmingham campus tomorrow from 8 to 12. Well, we had to schedule a meeting, department meeting, but I scheduled that for 12 so it wouldn't interfere with office hours. And then here came another conflict with that, so I had to move the department meeting to 9, and then I have to leave for the other one about 10:30. So basically my office hours have been reduced to about 8 to 9. I will be in and out of the office a little bit around 10:30, but then I've got to leave to go to another meeting. So That's how Fridays go. Now that meeting, I don't know if any of you have heard about this. It's not an official Lawson State meeting, but it's something that my wife and I support. It's normally I wouldn't say this, but it's a school strike. Have y'all heard about it? Okay, it's for the environment, and it's going to be somewhere near Lynn Park, maybe in Lynn Park, somewhere there, and it's going to be tomorrow morning at 11 o'clock. So if you happen to be free then, go down and see. I think it'll be quite impressive. Mostly high school students, but they would welcome college students as well. And then there'll be a few old adults like me too, that are there, I'm sure. But one of the leaders in the Birmingham area, the one that I've heard the most from, the woman, student named Stella Tarrant. Now, our previous horticulture instructor, who was here before they canceled the program, he was Trey Tarrant, and he had a daughter named Stella. Now, how many other Stella Tarrants could there be in Birmingham? And she would be about the age to be a high school student now. So I think she's the leader of it. So that's another reason I feel sort of obligated. I don't know her personally, but I do know her folks, and they are good people. So 11 o'clock tomorrow morning. If you don't have anything else, please consider going somewhere near Lynn Park, and I think you'll see the crowd, and go for it. Support, because our environment's in serious danger, and we're doing things not making it any better, making it worse. So the students are fired up about it, so I'd say get fired up too. I'm going to try to, and as old as I am. Okay. All right, where we left off. Any questions? Anything that we've covered so far? Okay, we're in finishing up. We're in Chapter 1, Functions of the Graph, 1.6. We finished the section except for the vocabulary. So if you can turn to page 65, top of the page, 10 questions there. The first 9 are write the most specific name of these functions. Now, if you don't have a book, last person then close the door. Sorry, I forgot to. Sorry, get out. Sorry, we gave it the office. No, don't pull the door all the way through. Last person did. Okay. Is it Daquan? Yeah. All right. Anyone else come in since the call roll? All right, and since we'll be continuing Chapter 1, Functions in the Graph, we'll be starting 1.7 after we do the vocabulary for 1.6. And since not everybody has a book in front of them, I'll write these. I'm not going to write the f of x. I'll just write what this function is, if I can get it done. Huh? Womack, got it. Sierra. Okay. I'm sorry? Okay, I know. We just have vocabulary to do. Yeah, and it's not got a slide, so I went on to 1.7. And by the way, for any who have come in since I said it, if you haven't picked up your first quiz, please pick it up before you leave today. Okay? Those went out a week ago. Okay. So I'm going to just write down the function. I'm not going to put the f of x, and you tell me the most specific name for the function. Let me get my pen set up. Okay. If you can read that. What is that function? This one. Oh boy, how soon we forget. At least, huh? Greatest integer function, perfect. Number 2. This may be tricky. F of x equal x. The what? I think someone said it right. I just can't hear well. Help me. I'm up here drowning. Identity function. Perfect. Okay. F of x equal 1 over x. Anybody? It's the vocabulary top of page 65. Right at the end of 1.6. Yes, these are parent functions. Okay? What is number 3 here? 1 over x. Oh, 2 days, it was a long time ago, wasn't it? What's that one called? Reciprocal function. Perfect. Okay, how about this one? Oh, this is hard. The squaring function. Perfect. Okay. How about this one? Another hard one. The square root function. Okay. How about this one? F of x equal c. Constant function. Excellent. Okay. How about this one? We didn't actually do it much in class, but they showed it right at the end. Second. Absolute value function. Perfect. And this one? The cubic function. And this one? Second. Did I hear a linear function? Yes. Okay, you got it. Now, number 10, fill in the blank. The constant function and the identity function are 2 special types of blank functions. Linear functions. Perfect. These 3 here are technically all linear functions. The constant function is a horizontal line. The identity function is a 45-degree line, and the ax plus b can have any slope at all. Okay. I think I assigned all the homework exercises to you from 1.6. Any questions on those? All right. If not, we're moving to 1.7. 1.7 is going to talk about transforming functions. We've got the parent functions, the basic functions down. Now we're going to start manipulating them, messing with them, transforming them. Okay? We'll use vertical. Just close the door again. I don't know why they locked the door. Okay. I'm sorry. I'm going to pull it too. Just don't pull it too all the way. Unless you know who's coming next. Ah, yeah. You could have. No, I'm sorry. Don't pull it all the way too. All right. Cammy, I thought so. Okay. And Josh. Okay. Good deal. Anyone else come in since the code roll? And again, if you came in after I made the announcement earlier, be sure before you leave today, if you haven't picked up your quiz, that you do so. Okay? Quiz 1. All right. So the objectives in 1.7 use vertical and horizontal shifts to sketch graphs of functions. Now, a lot of this is focusing on sketching graphs, and if you haven't picked up on it now, this author of this book loves sketching graphs. Okay, so we'll use vertical and horizontal shifts to sketch graphs of functions. We'll use reflections to sketch graphs of functions. And then we'll get to what they call non-rigid transformations. Guess why? To sketch graphs of functions. Okay. So let's talk about these shifting graphs here. Okay, graphs here. Many functions have graphs that are transformations of those parent graphs. For instance, here's one very simple one. Here's h of x is equal to x squared. Now, what would be the parent graph, parent function for that? Say again? X squared. Okay. That would be the parent function. How does it look? Has a name. That shape has a name. We didn't focus. A parabola, exactly. Tell me a few things about that parabola. It's what? Okay, it's like a U. Where do you find it? What's its x-intercept, for instance? 0, 0. X and y-intercept is 0, 0. Okay? Opening which way? The U is opening upward. Okay? You said that sort of. Okay? Now, what are we doing to it? Adding 2. So picture that parabola, that U-shaped thing at the origin, and what do? You shift it up 2 units. That's what you do, because this function here, the x squared function, adding 2 to every value in it. And this is what it looks like then. Here is your parent function, alpha of x equal x squared. Add 2 to it. Ding, ding, ding. Goes up to every point. 0, 0 goes up to 0, 2. 1, 1 goes up to 1, 3. Negative 1, 1 goes up to 1, 3. Okay? Wherever it is, right there. Okay? 2, 4 goes up to 2, 6. Somewhere about there. You can't see it, but you see every point shifts up by 2. By shifting the graph of f of x equal x squared, the parent function, up 2 units, shown in this figure. Okay? Any question? Vertical shift. Pretty straightforward. Could this shift downward? How? A -2. That would drag, or -1 or -0.3 or whatever. Okay? Anything you would subtract would shift it downward. Same shape, just shifted up or down. Okay? That's a vertical shift. Now, the key here is the parent function. That's what you're adding to. Because the function itself is which? F of x is? F of x is y. Okay. And if you add 2 to that f of x, you're going up the y-axis. Okay. Good deal. Now, in function notation, h and f are related. They're second cousins. Okay, no. Okay. H of x is x squared plus 2. But remember, f of x was x squared, so this is f of x plus 2. The y value for your parent function, up 2. Okay? Similarly, you can obtain a graph that is a horizontal shift. Now, if a vertical shift is adding or subtracting from the y value, what would a horizontal shift be doing? Okay, from the x value. But remember, x is part of your problem, isn't it? So now you add or subtract 2 from the x. Now, here's the problem with x's. Everything to do with x's, they're backwards. Okay? A x minus 2 squared, where do you think that would shift? No, that's y. To the right, okay? Even though minus, you would think went to, no, it goes to the right. It's always backwards, okay? Not backward enough to go up, but, okay. So you're shifting this to the right 2 units, okay? It's shown here. Now here's an easy way to check that. Figure out a value that makes this 0. That would be 2 minus 2, right? Well, 2, x equal 2 would be over here, so that's the shift to the right. Okay. Everything else is the same, just every x value is moved to the right 2. 0, 0 becomes 2, 0. 1, 1 becomes 3, 1. Negative 1, 1 becomes 1, 1. Everything is shifted to the right 2. 2, 4 would be shifted to the right to be 4, 4. Okay? Negative 2, 4 would be shifted to the right and becomes 0, 4. Everything shifted to the right 2 units. That's a horizontal shift. Okay? How do you think you could go the other way? Could you? How? Add it. Yeah, x plus 2 takes you to the left. Those x's are backward, aren't they? In this case, the functions f, g, and f have the following relationship. Now, remember, for a vertical shift, it was f of x plus or minus 2. For a g of x, it's f of x minus 2. It's not the function being added to or subtracted from, it's the x value itself. Because the function was a y value, the x, that's where you do the horizontal shift. So the following list summarizes this discussion about horizontal and vertical shifts. If c is a positive real number, all our c's are going to be positive here, okay? Vertical and horizontal shifts in the graph of y is equal to f of x are represented as follows. A vertical shift, c units up, what would that be? Y is equal to f of x is our parent function. Vertical shift, c units up would be f of x plus c. Perfect. C units down, f of x minus c. Horizontal shift, c units to the right, f of x minus 2. C, right, minus c. Okay. And a horizontal shift, c units to the left, f of x plus c. Perfect. Way to go. Y'all are good at this. Okay. Any questions? Is it kind of making sense? Okay. Some graphs can be obtained from combinations of vertical and horizontal shifts as demonstrated in example 1b. Don't get to that in a minute. Vertical and horizontal shifts generate what we call a family of functions, each with the same shape but different location in the plane. So that, yeah, all right. So I think we're ready. Amari? Okay. All right, good deal. Anyone else come in since I called off? Okay. Again, let me say for folks who may have come in late and didn't hear me say it earlier, if you haven't picked up your quiz for the first quiz, please pick it up before you leave today. All right. Most of you, I think, already have it. All right. So here's example 1. Use the graph of f of x is equal to x cubed. So y'all are going to need to help me draw this graph. Okay? Give me some points that are on f of x equal x cubed. Second? 0, 0, certainly there. Good old parent function. Next. Let me tick off a few points here. 1, 2, 3, 4, 5, 6, 7. Okay. Next. 1, 2, 3, 6, 7. Negative 1, 2. Not very evenly spaced. Okay. Give me another point. Got 0, 0. Give me an x. Second. 1. These are 1 and negative 1. 1. Okay. What would be the y value? 1. Okay. Give me another x. Second. 2. What would be your y value? Second. 2 cubed. 4 would be 2 squared. 8. Okay. So at 2 you'd be 1, 2, 3, 4, 5, 6, 7, maybe 8 somewhere up there. Whoa, going up pretty rapidly, isn't it? Okay, give me another x. I think I put it too far to the second. Ooh, okay, she wants me way off scale, isn't she? 3 would be what? 27. I don't think I can get there. Okay, so let's go the other way. Negative 1, what would that be? Negative 1, okay. Next, negative 2 would be a negative 8. That's off scale. So here's how that function looks. It comes up pretty abruptly here, evens out here, and then goes up pretty sharply there. Something like that. Okay? Now, how would I do g of x is equal x cubed plus 1? I need a color for that so we can distinguish. Pick me a color. Blue, light or dark? Second? Light? Okay, we'll do Carolina blue. Okay. How do I do G? Second? Second? Right one. Why right one? Second? Wait a minute. Down one, because you're subtracting from the function, from the y value. See, this is your y, okay? And you're subtracting from that, so that would be down one. So this one goes down one, that one goes down one, this one goes down one, this one goes down one. They all go down one. So now your curve is something like that, okay? Just like the other curves, kind of, just down one. Subtract one from each of those values. You can plug in values if you want to. Do all that calculation again? Yes, okay, but I'm lazy. I like to do it the easy way, okay? But if you want to work hard, you can still get it done. Okay, how about h of x? I need a different color for that. Pick me a color. Second? Yellow. Ooh, that's going to be hard to see. Okay, but let's see if we can see it. Okay? What are we doing with h? Left 2. Just don't say yours. Okay, yeah. Up 1. Okay? And we start with our original. That's left 2, up 1. I don't know if you can see that. There it is. Then this one goes up 2, left 1. That would be right here. And then, yeah, I think I did it right. Yeah, I just got a real long space right there. This one right here, I can't get up 2. This one I can go up 2 and I didn't do this one right. No wonder it looked bad. Why did you let me get away with that? Okay? No. I've been saying it backwards. I think I had that one right. Okay. Okay. I've been saying it backwards. It's left 2, up 1. Left 2, up 1. I had that one right. And then this one was left 2, up 1. That should have been here. So shame. Okay. Let's erase. If I can do it without erasing. I did. Okay. Everything. All right. And this one up here. Left 2 and up 1. We can't show that. This one down here. Left 2 and up 1. Right there. You have to use your imagination for the rest of it because they're off scale. But it's coming up here really sharply, evens out here, and then goes up like that. That one's going to be not that sharp. It's only going to go, yeah, up 2. That's how it looks. Same shape, if you can see that, of this one and that one. It's just that it's over here. It had a left 2 and up 1. Okay, everything was shifted left 2 and up. This one, left 2 and up 1. No. This one, left 2, up 1. From the parent function, the original function. Okay. All right. That's my ugly scratch. Let's see how they did it. I don't think they could get any better looking than that. Do you? Do you better? No. Never mind. All right. Relative to the graph, they do in the gray graph, they do f of x equal x cubed. Just pretty much like we did it, right? And then the next one is, the A part is down 1. That x cubed down 1. Subtract 1 from it. And everything goes down 1. This goes down 1. This goes down 1. This goes down 1. They all go down 1. So everything's depressed by 1. Downward shift 1 unit. shown there. Okay? Now the B one, they start with a new axis. We put it all on one. And this one, as you said, left 2, remember everything with the x is backwards, and then up 1. Okay? So here's your parent function, okay, the original x cubed, and we're going to go left 2 and up 1. There's that point. Here's this one, left 2, left 2 and up 1 right there, okay? And then this point was left 2 and up 1 right there. Okay. Sort of hard to see without the points in there. Make sense? Yes? Yeah, you draw the parent function and then you do your shifts from there. Yeah. Is that what you're asking? Yeah, we're not solving anything, we're just sketching graphs. Like I said, this author loves sketching graphs. Okay, so stand by for this just about everything. Had at least one on your quiz. I promise you will have at least one on a test. Okay. Every quiz, every test. Okay. At least one. So that was example 1. Okay. Let's move on to the next. In example 1b, you obtain the same result when you do the vertical shift first and then do the horizontal shift. Or when you do the horizontal shift and then do the vertical shift. It doesn't matter on your horizontal and vertical shifts. Some of the things it will matter a little bit. You have to be pretty careful on. And that's what we're going to get to. Maybe not right. Yeah, this next one is sort of important that way. When you start reflecting graphs. Another common type of transformation is a reflection. Okay? That's not when you stare in your navel, that's something else. Okay? For instance, if you consider the x-axis to be a mirror, then the graph of h of x is equal to minus x squared. You know what x squared is, right? That's a parabola up, like we started before, right? Now, what if you negate that? Now you make it a parabola down. Because 0 stays 0, but all the other values that were all positive now are all negative. Okay? And that, you treat the x-axis like a mirror, and whatever you had up here, now you have down there. Reflected across the x-axis. Okay? Make sense? That's negating the y. That's what, this is your y. F of x is the y. You negate all the y's. Every y up here, you put down here. Same x's, opposite y's. Every one of the y's is opposite. Okay? Now, all right, everybody got it? Okay. Now, they didn't show us the other, but I'll show it now. Okay? Reflections in the coordinate axes, y is equal to f of x, are represented as follows. Reflection of the x-axis is negate the y's. Well, reflection across the y-axis is negate the x's. Okay? Now, this looks a little bit like our even and odd test, doesn't it? And there's a reason for that. When the, not quite, but close, if this thing had come out the same, then that would have been an even function. If it come out exactly opposite, that's the odd function. It's not quite the same as this. This is just saying, now that the example we gave before of the parabola, reflect that about the y-axis, and it's the same parabola. So that's not much of a reflection. But if you had something like the cubic function, reflect that across the y-axis, then you have it going in the opposite direction. And an exact reflection across the y-axis. So f of x, if that's the cubic function of f of minus x, would then be reflecting across the y-axis. Okay. Now, here's example 2, and they give you way too much information. The graph of this function is shown here. Okay? Now, what does that look a lot like? A parabola. It's not for these two reasons. Near 0 is flatter than a parabola. Remember, a parabola came down, just touched it at 0 and went on up. This one hangs around 0 a bit longer. It's not 0, but it's closer to 0. And then on the outside, it's steeper. The parabola was a little more gently increasing and decreasing past that. This is really steep. Okay? So, but that is that's your parent function, a parent function, not one we dealt with, f of x equals x to the fourth. Now, what example 2 is asking you to do is, each of the following below is a transformation of the graph of f. Write the equation for each of these functions. That first one that we had here is f of x is equal to x to the fourth. Okay? What do you reckon this one is? What two things have you done to it? You had it on the same graph. The original x to the fourth looked like this. What's the first thing you did to that? You reflected it. And then you did what? Shifted up. So this one, the order does matter. Okay? So what it's asking you to do is write the equation for each of those. Remember your parent function. Let me see. Let me get my pen back. Okay. The parent function was f of x is equal to x to the fourth. Okay? And this one, the first thing you're going to do is the y is equal to g of x. The first thing you do is reflect, so that's going to be minus x to the fourth, but then you go up 2. So that would be plus 2. Does that make sense? Well, does that make sense? Not really. All right. So there is this g of x. Y is equal to g of x minus x fourth, reflect it, and then bump it up by 2. Okay, what did this one do? Second. Okay, y is equal to h of x, and what did you say it was? My hearing's bad. Okay, you reflect it first. Now, my whole thing went away. No. There it is, okay? You reflect it first, and how do you do that? Minus, but then you're doing what? Shifting to the right. How many? 3. So how do you express that? X minus 3 to the fourth power. There you have it. Okay? Very good. Now, you can check some of these if you wanted to. Give me an x. 0. 0 to the fourth power is 0. Negate that, you get 0 plus 2. 0 plus 2. There you are. Right there. When x is equal to 1, 1 to the fourth is 1. Negate that, you get minus 1. Add 2 to it, and you're right there at plus 1. So 1, 1. Yeah. You can do it that way, but it's so much easier to just do your shift. Okay? Especially coming up with the equations. You can check them fairly easily. Boy, I would hate to try to do the equation any other way than using the shifts. You first negate, and then you shift. Okay. Remember, x's go backwards. Okay. So notice they're having you do both ways. They give you a function, and then you say, draw the graph, or they draw the graph and say, you come up with the function. So be able to go both ways on those. Okay. And by the way, I haven't been saying it, every example has a checkpoint. So be sure you do the checkpoints as soon as you can outside of class. Let's check and see how they did it. The graph of G, that was the first one that we did, is a reflection in the x-axis followed by an upper shift of 2. So that would be a minus x to the fourth plus 2, just like you got. Okay? The B part, the graph of H, was a horizontal shift, I wish they hadn't said that, of 3 units, followed by a reflection. It's okay in this case to do that, okay? But I like to say you reflect first and then shift, okay? Because if you had said the same thing here, if you had said shift first and then reflect, you're not reflecting about the x-axis, y-axis, and x-axis in this case, you would have been reflecting about the vertex up here. So that's why I think to say the shift first, followed by the reflection first, followed by the shift. Okay? They got away with it down here because it was all right. You didn't leave the x-axis. But really, I would have reflected first and then shifted. Okay? So that gave you minus x minus 3 raised to the 4th power. So reflection first, right shift 3. All right. When sketching the graphs of functions involving square roots, remember that you must restrict the domain to exclude negative numbers inside the radical. Okay? That's the key. For instance, here are the domains of these functions. Okay? All right. Domain of g of x, which is minus the square root of x. What would be its domain? X. Tell me. It's what? Greater than or equal to 0. You can't take the square root of a negative number. So x has to be greater than or equal to 0. How about that? Can you say, wait a minute, you can't do that, you can't take the square root of a negative number? No, you can't. But x could be negative, and then minus a minus is a plus. So what's the domain of that? X is less than or equal to 0, because you flipped everything. How about this one? What's the domain here? A little louder. Okay. Domain would be what's inside here. X plus 2 has to be positive, greater than or equal to 0. Okay? I can't write it without you seeing it, but I'll let you see it. Okay? Here's how I do this. You look at what's inside the radical, x plus 2. What's inside the radical has to be greater than or equal to 0. Always, always, inside a radical. Now what do you do? Solve the inequality for x, isolate the x, subtract 2 from both sides. And that gives us x is greater than or equal to negative 2. And that's what we got there. So it's you don't have to strain your brain. Just figure out what has to be true. Whatever's in the radical has to be positive, greater than or equal to 0. Then solve the inequality. Okay. Now, what they didn't do is what's the range of these? What's the range of this one? Range of this one? The first one. Negative y's, because the radical always means principal square root. But when you put a minus in front of it, that means you flipped it across the axis, so it's now negative. How about that one? The range. I don't need to cover that. What's the range of that? All positive, because it's a principal square root. So your domain will be negative, but your range will be positive. How about this one? Yes, you're negative again, because this means positive. This makes it negative. You're absolutely right. So we could, let's see if they draw the graphs of those. No, they don't. Okay, let me just quickly show you what that looks like, if I can do anything quickly. Okay. Let me erase this, because it's already written there. Okay. Now, here's what the graph looks like. Okay. Here's 0, 0, 1, negative 2, 1, 2, 3, 4, 5, 6. Way more than I need. Okay? And we'll do minus 1, 2, 3, 4. 4. Okay. When x equals negative 2, that's as low as you can go. That's 0 then, because x equals negative 2 would be 0. X equals negative 1, you'll be right here. X equal, you want what's inside there to be a 4. So that would be positive 2. Okay? X equals positive 2, that would be a negative 2 here. And then you keep on going. You want what's in there to be a 9, so you 7. 1, 2, 3, 4, 5, 6, 7. Here that would be a minus 3. Okay. So here would be, you remember how the square root function looked? Half of a sleeping parabola. Okay. Because this is shifted to the left 2. Okay. Because x plus 2, that's to the left 2. And then it reflected downward. So it's like this. Or you could have said it reflected first and then shifted down. Shifted. So our parent function looked like that. This one reflected and shifted to left. To left. So this is what it looks like. I did it the hard way. If you had done the shifting, you would have seen this. But they didn't show the graph, so I just showed it that way. Oh, they did, well, you know what they did? They took example 3 and just made it not an example, but they just showed the 3 things, the domain. What I've just done, or not quite just done, let's go back and do the same thing to all of these. Okay, so I'm going to, let's do, okay. Give me a color for the top one here, G of X. Different color. Red, okay. Dark red or light red? Dark, okay. Now, oh my goodness. This is G of X is going to be our red one. What have we done there? I probably should do the parent function. So give me another color for the parent function. That's it. Give me. Second? Purple, okay. Purple parent function, okay. The parent function, 0, 0, 1, 1. Now I've got to put some things up here. 4, 1, 2, 3, 4, 2. And 9, 3. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, somewhere up here. Up there. So here's your parent function, half of a sleeping parabola, okay? Right? There's a parent function. We've already done K, the third one. That was number 1, you reflected, and number 2, you shifted 2 to the left. That's this one. K is the black one, okay? This is K, this one down here. Okay, so let's go back to the red, dark red, okay? What's your G going to look like? Say again? Flipped, okay? Across which axis? The x-axis. So it's 0, 0. Everything's flipped across the x-axis. Down here, and this one's down there. Okay, somewhere like that. So here's what it looks like. It completes that sleeping parabola, doesn't it? Okay? Because it's just the bottom half of it. Okay, how about the H? What color you want H to be? Green. Light or dark? Light? Okay, maybe a little hard to see, but we'll see. So what's H going to be? That's not too hard to see. This one's not going to show up too well. What are you doing? Yes, you're reflecting across the y-axis, so you go 0, 0, negative 1, 1, and you go like this. So it's this purple one reflected across the y-axis. So it goes over like that. Make sense? That was example 3. They left it off the slide set. They just did talking about domains here. Okay. Now, there is a checkpoint after that one. This would be a very good checkpoint to do. Okay? Now we're moving to non-rigid transformations. The ones we've done so far kept their shape. Okay? The shifting kept the shape that just went up and down, right or left. The reflecting kept the shape that just reflected across the X or reflected across the Y. But they kept the shape. The non-rigids, they stretch or compress, or they don't quite keep the shape. They keep the basic shape, but they distort, I guess is the best way to say it. So horizontal shifts, vertical shifts, and reflections are all rigid transformations because the basic shape of the graph is unchanged. But those transformations change only the position of the graph. They shift it right, left, up, down, or reflect across X or reflect across Y. Okay? But they keep the shape. They only change position. The non-rigid transformations are those that cause a distortion. They stretch or they compress. One of those. Okay? So, for instance, a non-rigid transformation of the graph of y is equal to f of x would be represented by, and remember, our transformations were by adding or subtracting positive numbers or negative numbers, okay? Adding or subtracting. Our non-rigid are going to involve multiplying or dividing by some constant, okay? So if you have y is equal to f of x, then you have g is equal to c times f of x. Every f value that you had here is going to be multiplied by c. So that's going to be a vertical stretch. If c is greater than 1, but if c is between 0 and 1, it's going to be a vertical shrink because you are multiplying either a big number by f of x, which would be a stretch, or a small number, still positive number, and which would be a vertical shrink. Okay? And that's not a psychologist that lives on the bench. No, not a vertical shrink. Okay. Another non-rigid transformation of the graph y is equal to f of x is represented. This time we don't do the c to the f function, to the y value. We do the c to the x value. So it's f of cx. Okay? That's going to be a horizontal distortion. Okay? Now, what you think a large C is going to do to you? Going to be a shrink or a stretch? A large C. Say again? Shrink, because everything you do with x's is backwards. So a large C up here is a stretch. A large C down here is a shrink. Okay? Whereas a small c, something between 0 and 1, is a stretch, because everything you do to the x's is backwards. Okay? So it's a horizontal stretch when c is between 0 and 1, is a horizontal shrink when c is greater than 1. C's are always positive, by the way. Okay? Now, that's the general stuff. And let me close the door, but not all the way. I don't want to bother everybody up and down the hall. Just some people. Miss Martin next door, I don't mind bothering her. Okay. I haven't got my watch out, so I know y'all would just let me talk forever, wouldn't you? All right. Compare the graph of each of the function with the graph of f of x. Ooh, what's that graph? What's that function? Absolute value function. So we need to draw the absolute value function first. So let's draw that in black. Okay. Okay. I'll tick off a few points here. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. How does the absolute value function look? It's a V. At 0, 0, 1, 1, it's the identity function to the right. 2, 2, 3, 3, it's a identity function this way, and the opposite of the identity function this way. Okay. So, there is your f of x equal absolute value of x. Now, what color you want h to be? So, orange? Okay. Aren't you nice? Okay, never mind. Okay. I didn't say that, did I? Okay. How will we do that? What is that doing? H of x is equal to 3 times absolute value of x. Vertical stretch, okay? Because for every x, for every f value you have here, the y's on this one, you're multiplying by 3. So 3 times 0 is 0, but 3 times 1 is 3. 3 times minus 1, this is also a 1 here. 3 times 1 is 3. 3 times 2 is 6. Okay? 3 times this 2 is 6. 3 times 3 is 9. Somewhere up here. I think that one was 9. Okay? And this would be a 9. I probably went too far over there. So here we have it. Now, I don't know if y'all remember those little weird little string toys. When you let it go, they just flop. But then when you pulled it, they stood up or raised their hands or something. Y'all don't remember it. So this is like you're pulling the string up, and now you make it stretch vertical. That didn't do any good. All right, you stretch this vertical. All right. H of x equal 3 times the absolute value of x. How about g of x? What color you want that one to be? Second? Blue. Okay, you want light or dark? Dark. Okay, dark blue. Okay. On this one, you're multiplying again, so it's going to be vertical, okay, because you're multiplying to the f function, but now you're multiplying by 1/3. So what does that become? 1/3 of 0 was 0. 1/3 of 1 is 1/3. 1/3 of 2 is 2/3. 1/3 of 3 is 1. Something like that. 1/3 of 4 is 4/3. 5/3. 6/3, which is 2. 7/3. And over here, 1/3 of 1 is 1/3. You multiply by the y value of this, okay? So it's 1/3, 2/3, 3/3, which is 1, 4/3, 5/3, 6/3, which is 2. I'm up too high. Okay. So here we have it. That's ugly. Okay. That's a vertical shrink because you're multiplying by a number less than 1. Still positive, but less than 1. So a vertical stretch is when that C is greater than 1. A vertical shrink is when the C is between 0 and 1. Does that make sense? In other words, an elephant sat on the first one. Just squished it out there. Okay. Make sense? All right. Let's see how they did it. I'm trying to sit so y'all can see a little better. Okay. Okay, I think I'm going to have to remove my scratch for you to read that. Okay. So for the A part, relative to this graph, which was our gray graph here, they like to do the parent function in gray, the graph of h of x, which is 3 times that, takes every y value for this one and multiplies 3 by it. The y here was 0. 3 times 0 is 0. The y here was 1. That becomes a 3. Y here was 1. That becomes a 3. Okay? The y here was 2. 2 times 3 is 6. That would be somewhere up here and there. So you stretched it by a factor of 3. Okay? A vertical stretch by a factor of 3. Make sense? However, if you had multiplied by a number between 0 and 1, then that means you're shrinking it vertically. Okay? 1/3 of what the f of x value were, or the y values. So this was 0, 0. 1/3 of 0 is still 0. 1/3 of 1 is 1/3. 1/3 of 2 is 2/3. 1/3 of 3 is, you can't see it. I'm sorry, 1/3 of 3. 3 was here, and 1/3 of that is 1, which is right across here. You can't see the 3 because it didn't go out that far. But every one is shrunk by a factor of 1/3. So that's a vertical shrink by a factor of 1/3. Multiplied by 1/3. Every vertical value. Any questions? Okay. Oh, what a shame. They left off example 5. Okay. I think we have time to do it. So let's find some white space. I think that's about the only white space we got. We go back to black. Back to black if I can get it to go there. Okay. Now, example 5. Compare and graph each function with the graph of f of x is equal to x squared. So you're going to have to tell me how to graph f of x is equal to x squared. Let me tick off a few points. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. Positive 1, 2, 3, 6, 7, 8, 9, 10. Okay, something like that. Okay? Let me write it down. F of x is equal to x squared. There's our parent function. Give me some points. 0, 0. Good deal. Another one? Negative 1 what? 1. Okay. 1, 1. Good. How about 2? 2 what? 4, is that what you said? Perfect. How about negative 2? 4. How about 3? 6, 7, 8, 9. There, we got a 9 up there. 3, 9, and negative 3? 9. Okay. In German, that's no. Okay, but it's yes here. Okay. So here is your parabola. Nice, smooth curve here. Absolute values are pointed. Parabola are smooth. U-shaped, remember? Okay. So there's your parent function. F of x is equal to where was I reading? No, I was reading the checkpoint. Sorry. I was reading checkpoint under 4. This isn't the problem. Erase all that. Okay. Yeah. Example 5. And by the way, you can go to larsonprecalculus.com and see an interactive version of this type of example. Okay? So compare the graph of each function with the graph of f of x is equal to 2 minus x cubed. You know, we got some work to do on this one. F of x is equal to 2 minus x cubed. That's not really a parent function. That's the function we're going to start with. We have to figure out how to draw that one. So you tell me how we're going to do that. Okay? First, let's just dot in what the x cubed function is going to look like. Ooh, this is a dilly, okay? Hopefully it'll come back. Did it? Yeah, okay. Now, the x cubed function would look like this. Notice the sound effects? Okay. Something like that. No curve there. Okay, that's the x cubed function, right? But we're going to negate it, right? So that's going to make it go like this. Okay, like that. So I'm going to wipe out the parent function because I don't want it to be confusing. Okay? So there is our minus x cubed. Then what are we going to do with that? Add 2 to it. So what is that going to do? That's going to bring us up to there, bring us up to there, bring us up to there. I went too high on this one. Not that one. There. Okay. Not there. Let me erase that. No. I erased the wrong one. Okay. Right there. Okay. Get out of there. Okay. This is the messiest thing. I don't think I can get the next point in there. 1, 2, 3, 4. Yeah. So here is what my actual F is looking like. Something like that. Not exactly, but close. So I'm going to get rid of my scratch work here. Okay. So there's our parent, not our parent function, but our beginning function. Okay. Now, what are we going to do with that? Yuck. Give me a color for G. Give me a color for G. Say again? Red. Light or dark? Dark. Okay. Here's our G function. G of x is equal to f of 2x. What is that going to be doing? What does this do to that function? This is our f function right here. What is this going to do to it? Say again? I thought I heard someone say it. Say again. Shrink it. You got it. Because remember, x is everything backwards. You multiply it by a number greater than 1, that's going to be a shrink. So every y value is going to be shrunk by half. Okay? So half of 0 is still 0. Half of 1 is going to be, it's going to keep the same x value, but it's going to be, the y is, how do I say that? Keep the same y value and shrink the x by 2. That's what we're doing. So this would be there. Okay? Horizontal shrink. So this one will be like this. We don't have many points to go from, but this is what it would be like. Okay? Something like that's a really ugly curve there. Okay? Everything is split in half. Horizontal shrink by 1/2. Okay? Everything horizontally is split by shrunk. So give me a color for H. Help me, somebody. Blue, light or dark? Light. Back to Carolina blue. Okay? Here's my H function. Hope you can read it. H of x is going to be f of 1/2 of x. Okay? So what is this going to be? A what? Yes, it's going to be a horizontal stretch. Horizontal because you're dealing with the x, but a stretch because you're multiplying by a small number. So every y stays the same, but the x's get doubled. Well, twice 0 is 0, but twice 1 is 2. Twice this one is also 2. Y stay the same, and you go from there. So basically this one is looking like that. Every x is doubled, keeping the same y's. It's a horizontal stretch because you're multiplying by a small number, multiplying the x by a small number. And if you check in your book, you'll see theirs looks almost as pretty, okay? Everybody see that? There's a checkpoint there. That's a checkpoint well worth doing. And guess what we did? We finished 1.7. Homework exercises here. We're not going to have time for the vocabulary, so we'll start there next time. Okay. Get my pages in place. Homework exercises, do either 5 or 7. They should both be at Calc Chat. Do 9. It should be at Calc Chat. Do either 11 or 13. They should be at Calc Chat. Then do any of the odds 15 to 19. They should be at Calc Chat. 15 should be at Calc View. Any of the odds 21 to 37. They should all be at Calc Chat. 21 should be at Calc View. Do any of the odds 39 to 45. They're all at Calc Chat. 39's at Calc View. Now notice on these, 21 to 37, they're giving you the equation, you describe, you write out what the transformations are. 39 to 47, they are 45, they're writing it out, you draw the graph, or you write the equation. So they're exactly opposite of each other. Then do either 47 or 49, they should both be at Calc Chat. Do any of the odds 51 to 55, they should all be at Calc Chat. 57 or 59, they should be at Calc Chat. 61 should be at Calc Chat. Then they have a couple true false, 63 or 65, they should be at Calc Chat. And then 67 should be at Calc Chat. 69 is an error analysis. I really don't like those too much, but think through those, because something's wrong with that picture. So I hate for them to put something wrong in the book, but it is. You figure out what it is. 71 should be at Calc Chat, and that's the last one. And those are on pages 72, 73, 74, and 75. 72 to 75. And then next time we'll start with the vocabulary and then move to 1.8. So folks, we're making good progress. That means the first test is coming up relatively soon. For those of you who did not get your first quiz, be sure you get it before you leave today. Anyone need it? Anyone need the first quiz? Yes. Everybody got it? You do. You need graph paper? Okay. Sorry? Am I going to be working? Here? Oh yeah, that'll be fine. If there's not due until Tuesday, but it'll be fine. There we go. Anyone else need the first quiz? Everybody got it? Okay, good deal. Wow. Okay. Paper? Yeah. Excellent. Okay. And those are, yeah. Excellent.